Okay.
Okay, so yeah, I would like to welcome Deepak Pathak. He's assistant professor at Carnegie Mellon University. He received his PhD from UC Berkeley and already early in his career made some substantial contributions to the field of deep reinforcement learning, perhaps most notably demonstrating the use of curiosity as a powerful intrinsic motivation for learning. And I'm looking forward to hear more about your exciting research now.
Thank you so much, Vivian, for inviting me to this workshop and for the introduction. And my internet is a bit weak, so what I'll do is, I know it will break in between, so I'll just turn off my video and then so that my slides play fine. Okay. So in today's talk, I'll talk about ontogeny and phylogeny of embodied robots. Now, what these terms mean, this will become as the talk goes, but just to give a preview, ontogeny basically means learning during the lifetime of an agent, and phylogeny refers to learning at an evolutionary scale. Maybe it could refer to the thing that we are probably born with in the very initial days. Okay, so before I start my talk, let me just state the fact or the principle which guides most of my research. And what I really believe is that the hallmark of human intelligence is our ability to generalize and adapt to new environments. And this generalization basically makes us who we are. So let us see where we are with machine intelligence. Well, we have lots of great results in machine learning in the last several years, where you can play the complex games like Go, translate speech, recognize language from images, and maybe or have cars that can drive themselves. And they're not fully ready yet, but maybe soon. But if you look at these systems, in contrast to human intelligence, these artificially intelligent systems are not that intelligent. In fact, they are specific to what they are trained for. For instance, a system that can play the game of Go cannot really drive a car. It's a completely different system that do different things. But while as humans, we have no problem in doing any of these things at a good level, at a good scale. In fact, this problem, maybe it's like too impractical to play Go and drive a car together. So let me give you an example, which is the fundamental of machine learning, like one of the basic tasks, supervised learning, like machine learning 101. Even in a task like this, so let me just give a preview what this just means. Like for instance, the task here is to classify the dogs in images. Like given an image, you train a model to output the class in that image. Now, the way this works is that you show this model a bunch of images of dogs, which come from a data set, which is randomly split into training and test. So when you are done on the training set, you test this model on the test set, right? And we all know this result, that so we do really, really well. Artificial intelligent models have exceeded superhuman performance in these data sets, and it performs really, really well. But how well do these models generalize when I train them on something that is not seen by these models? So for instance, if I take this model and test on video from YouTube, like this dog running over here, this model completely fails to generalize. It finds things like cobra snake. It finds things like ray fish, flatworm. And this is not a joke. This is the best model. Like this is ResNet 50 trained on ImageNet, and look at how it performs, right? And the performance drops to a much lower number compared to what we see on the test set. So what is going on? Like why are these models performing so bad? Well, it's not that surprising, because these models are trained on ImageNet, where the objects are at the center of the screen, taken by photographers with a good perspective, have bias and things like that. But that's my whole point. And this is the major issue, that in machine learning, we think that our training and test distribution matches. And all our models are based on this phenomena that let the world be IID. But in real world, things change continuously all the time. And whenever that happens, no matter what you have trained their model on, it will fail to adapt to realistic scenarios. And this generalization issue is not only in passive tasks like vision or language recognition. It is even more escalated in case of robotics. For instance, we have robots that can do all sort of these parlor tricks, like these amazing capabilities shown by this robot. But as complex as a robot, they fail to generalize to a simple task of putting a block on the table. And the failures in this case are even more catastrophic yeah, so it can really cost each failure. Each failure can cost really to the PI. So the real question is, humans can do generalization really well, adapt to well task. So how do you bring this generalization to machines, or how do you generalize beyond what you've trained for? How do you adapt fast? And this is what the whole talk will focus on. So let me begin by giving a simple example just to ground things in. So let's say here is a robot, and the robot is trying to tie this knot. It sees this image. Its goal is to tie the knot to this image, right? And it has to output actions to perform this task. Now, how do we train such a robot today? The most common approach is basically same as supervised learning, or in case of robotics, it's called imitation learning, where you get a human, and human tediously controls the robot, collects the full demonstration, like you see here. It collects all the actions that the robot should apply to do this task. And then you train the policy by supervised learning. But this is very tedious for the expert. But the bigger problem is the same process has to be repeated for every new goal and every new task, because there is no generalization here. You are training for that one task. So there is this other line of approach, family of algorithms called reinforcement learning, where the idea is that, oh, let's not worry about having an expert for each task. Let the robot learn it by themselves. So they start by this current image. They have this, the goal is to train a policy, such that output actions that leads to this goal image at the very end. And you get a reward when you go there. And the way it works is by training the policy to maximize the reward. Okay, everyone knows about this. But in this case also, there is one catch. And the catch is there is no expert to begin with. So the policy in the beginning is random. Now, if this policy is random, just think about it. How likely is it the case that it will reach this goal even once, right? It is extremely unlikely. In fact, by some estimate, in this setup that I'm showing here, it will take these many interactions to reach that state once. This is maybe like, I don't know, year to for a robot. And so there is no way that the robot will even see the reward. So this algorithm is kind of hopeless in this very sparse reward scenarios. So how does it work in practice? Because there is a lot of research going on for years, and this is one of the most popular area in AI. But the catch is that the story in practice is not so glorious. So for instance, if you look at this game over here, an AI agent is playing the game by looking at the pixels of the screen, it does get high score, but it relies on the score of the game as a supervision, which provides reward at almost every time step. So this is a very, very dense supervision. And in fact, in cases like navigation, where the agent has to reach some goal location, approaches today incentivize the cost function by providing apples in between, which are basically just there to guide the agent, because it cannot discover the end goal on its agent. But real world does not give you apples. In the real world, the reward could be delayed by days, months, or years, such that it's hard to propagate back to where you are. So how does this child over here know how to act to become pilot 20 years later, right? Well, psychologists argue kind of in the opposite direction. They say these babies or these infants are actually not guided by the extrinsic goal at all. Most of the learning in these agents is basically intrinsically driven by their own curiosity. For instance, this kid is trying to play Lego block here, not worrying about getting a job at Google 20 years later. It's like basically doing what thinks is fun. And what's the purpose of these things? The purpose is that by doing what you enjoy, you are learning skills which can in the future be used to guide to solve future tasks. Okay, so and this notion of learning without goals, learning without any extrinsic objective, is not just for babies. In fact, this is seen across almost every intelligent species out there. So this is a very good example given by Alison Gopnik, that of a contrast between a chicken and a crow. So on the left, you see a domestic chicken, which is considered one of the dumbest bird on the planet. So what they do is they come from egg pecking for grains, and they peck for grains all their life. That's all they do. There's nothing else they do. On the right, you have these crows, these New Caledonian crows, which are one of the smartest animals on the planet, and actually as smart as chimpanzees in many aspects. And they have similar brain size, similar cortical structure as chicken, but they are really, really smart, and they can pick food out of the test tube and do several things. So what is And there are several papers written on the new academic roles, like how smart they are and what abilities they have tool use, they have meta tool use, and all these things, despite the similar cortical structure. So what is going on? Well, what these psychologists argue, especially Alison Gopnik and Mertzov, is that this is because they have long childhood where they explore without goals. So crows have almost 1 year to 1.5 years of childhood, which is really long time in the lifetime of a bird. While in chicken, the childhood is probably just 1 day. I mean, they peck for maybe like they peck for grains, and that's what they do from the beginning, right? And this phenomena of long childhood and how intelligent the species is, there's a stark correlation over here. So as we see in this seminal paper from Piantadosi and Kate, where you can see this is across the primate species, where there's a correlation between the weaning time, which is x-axis, and intelligence of the species, with y-axis. So basically, the conjecture for this talk, or the first half of this talk, is that perhaps this notion of learning without being focused on one external goal is maybe not just an artifact. Maybe this is the reason that makes us generalize. Because if there is no goal, you cannot really overfit to anything, because you are not trying to do satisfy some external objective. You are learning what you enjoy, and you are learning skills. So but the question becomes then, in case of AI, if we have to build agents or do something interesting, the question becomes, okay, what do you even do if there is no goal? Like how, like, can you somehow implement this notion of goal-free exploration, curiosity, and text motivation? And this is kind of contrary to much of the learning that happens in machine learning, which is focused for a fixed goal, fixed task, fixed objective. So let me first go briefly into this question, actually what can we do? And this is something which I've been focusing on for past several years. And before I convey the high-level idea, let me first describe that there has been a lot of literature in the last 2 decades or even more in this area of trying to build exploration systems. But most of these works are trying to build algorithms for exploration in the context of some sparse end goal. Like, I want to go to this, I want to pick up this gold from some corner. Now, how do I explore in the context of that? And what we are really interested in, can you learn skills even without having access to any external goal, not just sparse, no goal, correct? So I'll not go into the too much detail of how do we do this, because this work has been going for 2-3 years. So what I want to focus today on is some of the new work or some of the new ideas in this domain. But before I go there, let me first give a high-level idea of how do we build these things in agents. So I'm calling it computational model of curiosity, and curiosity is in quotes just to disambiguate it from its. I do not mean to say this is the way how humans are curious or babies are curious. It's just a phrase here to refer to the kind of behavior that allows you to gain information from the environment without having any supervision from humans or anyone else. So what do we do? Well, the way the algorithms usually work is first agent goes and explores the environment and trains a model of how the world works. And this could be like, if I go into an environment and I see a box or something, I try to push it. So if I'm here, if I'm at some state, I take some action, what will happen next? So you build a model of that. And then you use the model to make predictions of the consequences of your actions before you take the action. So like, what if I take a ball and throw it? What will happen? I can predict all those things. And whenever your prediction is high, prediction is bad, your prediction error is high, the agent becomes more curious. So bad prediction of your own model leads to high curiosity. And that's when the magic happens. So when the agent gets more curious, it goes back and redoes all the things which makes it curious. And when you redo the same thing again and again, you collect more and more data by doing the time. Like if it's like breaking a glass, you don't understand, you cannot predict that the glass will break. You'll keep breaking it and collect lots of examples. But at some point you will learn that if you do this, the glass will break. So it learns these actions. And whenever that happens, your error goes down, your curiosity goes down, then you find something else to be curious about. And this kind of behavior leads to very interesting behavior because this agent can learn continually on its own by just exploiting curiosity. So for instance, we have shown all these results in the past across a wide variety of environments where agent can learn to walk, it can learn to navigate, it can play all of these games without having any notion of reward or a score from these games. So for instance, on the right, there is a Mario game. I'm not showing results here. I'm sorry. I should have built some video. But the agent can cross 10 levels of the game without ever knowing about what the game is about, like what is the score of the game. Because if you remember yourself, like many people would have played Mario at least or heard of this game. Like when you first played the game, who goes and reads the rule book as to how to play the game? Or who goes and sees the score or have to increase the score? Actually, I didn't even see the score until I was very old, that there is a score in the game. We just go and play and try to see what's fun and then just learn how to play the game, right? And so this kind of algorithms can work really, really well. But in today's talk, I want to focus on something else. The main issue is that simulation and games do not capture how the real world behaves. And these algorithms, while they can work really well on all these simulation environments, they are still inefficient because they take millions of samples to learn this. Like you are doing the same thing thousands of times, and then you realize, oh, you should not be curious about this anymore. You have learned about this enough. Like even in the games like this, the agent dies multiple times until it learns how to be curious. So the question is, how do you scale these algorithms to real robot, and how do you go beyond their current system? So before I go to describing how do we scale these systems to real robot, let us first see what is wrong about this algorithm which makes these systems super inefficient. Okay, so let's take the same example over here as I described earlier. The agent sees some current image, and it has some policy. It outputs some action, and then action goes to next state. Correct? This is the standard how an agent acts. Like let's say the agent over here is a robot. Robot goes there. It has to pick up something. This tube over here. It applies an action, picks up robot. Now the way we define the curiosity part is that there is a prediction model, as I described earlier, which takes the current image and it takes the action and it outputs the next image. Okay. Now the way we define curiosity is this intrinsic reward, which is the difference in the prediction error. So the curiosity is defined by the ability of the agent to predict. So it has some estimate of the next state what will be, and you take a difference in the ground truth state. And then you train the policy to maximize this reward. So this is how I described the high level idea earlier. Now, if you notice one thing over here, one issue with this is that in order to compute how much you are curious about something, you have to actually take that action in the real world. So for instance, if I have to make this prediction of the next state, to compute the error, I need the ground truth next state. So the robot has to pick up the object in reality and then compute the error. Correct. Now, the question is, how do you optimize this? How do you optimize the model so that the agent is curious? Because this environment is black box, right? I do not know how to backprop through the environment. So all these fancy methods, like all these deep learning, SGD, these things just break because you cannot take gradient through this objective. Because the ground truth state, this XT, which is in red, is coming by acting in the environment. So it's a pretty hard optimization problem. And that's where the reinforcement learning algorithms come, this reinforce comes into play. Like you cannot take a direct gradient of these functions. So you approximate it in expectation basically by hit and trial in some ways until you get the right estimate of the objective, right? So that's why this is very inefficient. But in our case, since the reward is completely intrinsic, why do we have to rely on the reinforcement or reinforce objective? Because this algorithm is designed when the reward is given by the environment. Like the reward is probably score of the game, which you do not know how to backprop through, or reward is designed by some other engineer. Like, oh, if you do this way, I give you a candy. You cannot backprop through a candy, right? But in this case, this is all intrinsic. This is all going on inside the head of the agent. So can we replace this somehow to backprop through it? So what we do in this scenario is, instead of having, the idea is as follows. It's a very simple idea. Instead of building one model that I show over here, the agent tries to build a bunch of these models. So it builds like an ensemble of these models. Each of these models are trained in the same way. That is to minimize the prediction error. So you predict, and basically the same way you minimize the error. Okay. But we make one difference. We reformulate the notion of curiosity not to be error, but to be the disagreement between the output. So it basically says that now the curiosity is, how much do these models disagree with each other? Now, if you think about it, if the models are learning something new which they have not seen before, now if there is something which you have not seen before, the disagreement or the variance in the output will be high. And when that is the case, it's a good indication that, oh, you should be more curious about this. And when the variance is low, it's probably something which everyone has seen, right? So this is a classic quote that all happy families are alike and every unhappy family is unhappy in its own way. So if there is something new which you have not seen, you will be different in your own way. But if something which you have seen, the variance will be low and the curiosity will be low. So it's the same, it leads to the same behavior. But the nice part about this variance is that variance does not depend on the output. You can just compute the variance as the, variance does not depend on this xt plus 1. So there is no red term xt plus 1 here. It is just a disagreement between the model output. And when that happens, there is no direct dependency on the environment. So agent can just imagine, okay, oh, if I do this, this will happen. If I do this, this will happen. And then you just compute how much you disagree among your multiple models inside your brain. And you see, compare that and you see how do you. But this part is really, really easy to optimize because it can just directly the gradients through it. There is no outside interaction. You don't even have to pick the object. You can just say, okay, if I pick it, what will happen? If you can predict very clearly, it means variance is low. If you cannot, if you have different hypotheses, maybe you should try it and then see what happens. And when we do this, this kind of algorithm does scale to real robots very, very efficiently and can learn in few thousand samples compared to millions of samples. So before I show the real robot result, let me show an example of how do people currently collect data in robot for robot learning. So, and the most common approach is this random exploration. So as you see here, if I run random exploration on the robot, it does not even touch the table because there are so many things it can do in the table that it doesn't even touch the object randomly. So how does this exploration work in today's scenarios? If the robot does not even touch the object, how do you learn? Well, you might have noticed two things. One, that most of these works are from industry. So they have a robotic arm farm, where they collect hundreds of these robots to parallelize the process and increase the efficiency. But in academia, you cannot afford hundreds of robots. We just have one. The second thing is you put lots of objects at one location so that if the robot goes randomly, it can still pick up something in a random try. But here we made the problem harder by giving only few objects on the table so that randomly it cannot just go and hit it. But with the sample efficient disagreement-based curiosity, the agent actually can go and interact with the objects in a matter of few hours of exploration and few thousand samples. Yeah, so this is all good. But so far, so this is all, we talked about how can agents explore on their own, but this exploration is practically only useful if you can go from exploration phase to achieving goals. Like babies have to grow up at some point and perform some chores. Like no one can be ready for a whole life, no matter how much we want. So we do want to go from exploration phase to goal achieving phase. But the cool part is once you have the models that you are building through exploration, you can deploy planning to achieve goals. So the idea is, high level idea is really simple. You start by exploring the environment, collecting data, and you build models I just described. It could be a forward model, like what will happen next, or an inverse model. If I have this, if I have to go next state, what is the action between that? Because you can learn in a supervised manner from your own data. Then at test time, if someone gives you a goal, you can just plan for that goal using this model via standard control planning methods. The only part that is replaced is that in controls, the model is known and it's a ground truth model. Over here, the model is basically learned from the exploration. So all that is changing in the grand scheme of things is how do you collect data, which is online via curiosity. And as you collect data, you learn your models from this. And with this kind of approach, we can go back to our initial conundrum, which I started with, like how does this robot learn to tie a knot? But the thing is, the way we approach this problem is that robot never trains for tying a knot. All it does at training time, it just collects data by interacting with this rope. It can have many different examples, and then you learn a model from this, and then the same model is then used to perform tasks at test time by planning for it. So the robot never has seen the shape of knot before. But when you show one example of this knot at test time, just a video of human doing something, and actually in this work, we just show it 3 images or one, or even the end image of the goal, the robot can just use the same model, which is learned from exploration, and then roll it recursively. So it thinks, okay, if I am here, if I do this, if I go to next state, then I apply the same model, go to next state, and then you can see which action to take such that the end state aligns with this knot. So this is a generalization here. The robot itself never tied the knot, but it can plan for it at test time by looking at just the images. And the same idea can be applied to different kinds of robots. So for instance, over here, there is a robot which navigates. So we let this robot explore where students worked for 15 days. It collects some data. And then at test time, we put this robot in a new scenario, in a new floor, and ask it to, can you go to this goal image? And it can actually go to this and solve this in a simple task. So there are various methods out there in robotics which can do like this kind of navigation or SLAM-based approaches. But the cool part here is that these results are basically emergent, and the robot never trained for this kind of task. It basically, what it does at training time is just basically curiosity and exploration. The similar idea can be extended to things like looking at human videos at test time and use that to plan from robot's own perspective. Yeah, I just skip this and move to next. Okay, so how much time do I have right now? I guess 15, 20 minutes since the beginning, 5 minutes late.
Yes, so about 15 minutes, but
okay, 15 minutes.
The time including some time for questions. Otherwise, we'll have to move the questions into the panel session a bit.
Okay. I'll try to finish in 10, 15 minutes. Okay. So far, what we talked about is how can we train the robots without having any external goal and external things. But if we were to look at a bigger picture and like if we were able to build journalistic machines, how do we go towards that goal? So the current approaches can be summarized with this toy diagram. So let's say, one approach is basically to train these robots like an adult, like I described earlier. And the other approach is to describe, as argued by Turing also 50 years back, is instead of training the robots like an adult where you supervise for every new task, train them like a baby and without any goal and let the robot learn on its own. Now, there is still always a question here, like how much of an inspiration can we take from these high-level ideas, like learn like a baby? Because it is very clear from neuroscience or psychology's perspective that some things are learned and some things are born with. There is question of nature versus nurture. And for a human psychologist or a human or neuroscientist working for humans, it makes sense to be restricted to this timeline of babies to adult. But as computer scientists, it's not our goal. We don't do the hard work. The hard work is done by the computer. So we don't have to be restricted to this timeline. We can actually start much earlier in the timeline. We can go all the way back and start really, really early so that the generalization is even better because and robot can learn skills which are not just at the level of software, but also at the level of hardware. And this is what today's talk is about. So this part, which is learning, like curiosity and goal-less learning, is called ontogeny, which is learning which is happening during the lifetime of the agent. But a big part of this learning also happens pre-birth at an evolutionary scale, like your muscle memory and things like that, which is phylogeny. And so far, I talked about this aspect of learning. And now let me focus some part on this aspect as to how can we take inspiration from the ideas at an evolutionary scale and bring them to artificial intelligence or embodied robots. So if we were to take inspiration from this, like how early should we take inspiration from? How early do we go in the timeline? Well, I would say the earliest possible. So what is even earlier than this? Well, at the very, very beginning, so much like some sort of Big Bang or kind of a Big Bang of evolution, was this point in evolution when single cells combine to become multi-cells. And then one interesting thing happened at that moment. Things go from always competing to collaborating. And this notion of compositionality kind of emerges. And this compositionality has been very useful in language. But we are still far from having such compositional structures to be exploited in case of embodied active agents. And in fact, there is a lot of work in biology which shows interesting things in the last several years. So long before the brains evolved, there are a lot of things that are done by these just cells at the cellular level. So for instance, there is this amazing talk from Michael Levin at NeurIPS a couple of years back, where he shows that in these flat forms, the cells of the body capture the whole blueprint of the agent, including the brain. So there is nothing special about the brain. If you cut the agent at different parts, and like at the tail, and you confuse the cells at the tail that they are brain, they can grow a head at the tail. So this is kind of amazing that every cell in the body kind of has information. So what the argument is? The argument is that the intelligence is more behavioral, and the focus on brain is maybe good for humans. But in general, if you look at the evolutionary scale, the learning is happening throughout the body of the agent, and the control of the agent is fully modular through the body. And in fact, this kind of notion is seen in slime molds, where there is no notion of centralized brain or anything. Everything is decentralized throughout the body. And the most impressive example is these ants. Like if you talk to a biologist, they will say ant colony is a singular thing, not a plural. And these ants can display very complex behaviors in a distributed way. So how can it help? How can these ideas help our embodied robots? Well, this is something which I've been thinking about a lot, and how can we learn at an evolutionary scale? So to study these ideas, we designed a playground of agent, where we have this environment, and our robots in this environment are basically like cells. They are really, really stupid and dumb. What does that mean? That it is basically a cylinder and a motor. And all these can do is apply torque at the motor, and that's it. They cannot jump or they cannot do anything complex. But they have one ability, which is much like cells, is that they can combine with each other to become a new agent. And when they combine, they behave like a single agent. So when these things combine, and since it's a simulator and not a real world, we have to employ some method to combine these things together. So what we do is a magnet. So if they come close to together, they can combine each other via magnet, and they have the action. So it's the same setup. So fully the agency or the learning is happening at the level of these limbs. There is no notion of global brain or global policy for the agent. It's completely modular, fully decentralized, and each of the limb can decide how to join and how not to join. And it's fully local. So let's see this example of task of standing up. So if I take this agent over here, let's say there is only one agent, and if I apply vanilla reinforcement learning, so baseline, how does baseline work in this scenario? So it is a simulator, but to show that it is still a difficult simulator. So if I have one agent, RL can make this. So the goal is to stand up and go as high as possible. If you have three agents, it can still work. But if you keep increasing the number of limbs in the robot, it becomes very hard. And the reason is because as the number of limbs increase, your action space increases. So in contrast to that, what we do here, as I'm showing here, is that we allow the robots to stand up and combine with each other as the training goes. And when that happens, after training, these robots learn to combine to make more difficult tasks. So the question is, how do you? I got feedback. Okay, the question is, how do you learn these compositional controllers? And the key idea in this work is that, again, the modularity. So we share the policy across all limbs of the agent, and these policies are allowed to talk to each other. Okay, so let me see the time. Maybe I'll skip the approach in the interest of time. So basically what is happening is that the policy is shared across all these limbs, and what you want is the same policy to work at this level, at this limb, at all different places. I just go very fast. So the key idea is that the policy is shared, and since you want to apply policy at different locations of the agent, you want the policy to talk to each other. So what we do is we just allow the policy to take a message as input and they output a message which goes to a different agent. And then we arrange these policies in the same manner as the shape of the agent. So if the shape of the agent is this, we arrange these policies via this, and they can talk to each other via messages. Note, it's the same policy everywhere. The only thing that makes it different at different places is that it gets a different message here. So it gets a message from the bottom, it gets a message from here. And if the shape of the agent changes or it is a different agent, you just cut the policy from here and then you paste it here. And then this whole thing becomes a new policy. So much like a self-assembling agent like ant behavior or cells. And we call this dynamic graph network. So what we want to kind of do here is basically curriculum learning, where the agent starts from small limbs and gradually learns to become more complex. But this whole process is learned in an end-to-end manner. And this is basically curriculum learning, but happening in hardware and not only at the level of software. So what we found that if you learn from scratch the generalization, which was the eventual goal to go earlier in the timeline, actually improves quite a lot. So here are results of agent which learn the task of standing up and go as high as possible with 6 limbs, but now the policy can generalize to twice the number of limbs or even half the number of limbs, and it works better than a policy trained from scratch. You can also apply forces on the agent at test time, and it can take different shapes. You can apply the same idea for locomotion. So the goal here is to move to the right, not go up. And these agents learn from scratch by combining these limbs. So it makes a weird shape to move forward. Now the same policy can actually generalize to, if I change the terrain altogether. So over here, the same policy is able to cross hurdle at test time. So why is this happening? Why is it able to generalize so well to all these different terrains? Well, if you think about this, this policy was trained on a terrain which had some bumps and some bumpy surface. So a small agent, like a 3 or 4 limb agent trying to cross a bump is similar to a bigger agent trying to climb a hill. If your learning is happening at a modular scale, if it's compositional. So the argument of compositionality makes the generalization super easy. So it can actually go through the limbs and climb all these stairs. This is completely a test time, no training for these environments. Since the training is completely modular, it is also fine with losing a limb or two in the gap, but still move forward. Okay, so this idea is conceptually good, but it makes sense. And this was a Nurex paper which we did last year. But how can we extend this idea to normal robot? But humans do not shed limbs as they're moving, and this is not very impractical if we were to scale this to normal robots. So, and in fact, this phylogeny is also seen in many of the normal animals as well. Like there are examples of giraffe, horses. All these animals can basically start to walk as soon as they are born, which kind of suggests that they have learned this ability to walk through evolutionary timeline and not learned after they are born. So there must be a way to apply the same idea of learning at an evolutionary scale to also a normal robot. And that's what we do for these kind of normal robots, like these robots in simulator like Mojoko. And before I go to our result, let me show you what happens if you train a vanilla reinforcement learning in all these robots. So if you train for this robot, and even if you change one thing in the robot, like you removed 1 feet or something, this policy completely gets destroyed. It doesn't generalize at all. While all of the biological agents can actually still walk if there is some sprain in your leg. So what we do is that to handle this problem, we apply the same idea which I described earlier of learning in a modular way, but now instead of applying it on this weird shape-changing robot, we will apply it on a large variety of different kinds of robots with different shapes. So robots are no longer changing shape, but now the problem is much harder. What you want is you want to train a policy that can function across all these robots, such that this policy can generalize to new agents at test time, like this horses or giraffe, which can just walk out of the box without training, like no ontogeny, only phylogeny. Learn during life, learn before, and as soon as you get a new robot, it should be able to walk or do something interesting. So the approach is very similar. I'll just skip this and go to the jumps directly. And I'll just go to the results. So with the same idea of modularity, where you share the policy across the limbs of the agent and the policies can talk to each other via messages, these agents can learn to walk, and the same policy, same parameter, show a very different behavior depending on the shape of the agent. So this agent has one leg, it starts to hop. If it has two legs, it walks. It also has one leg. Again, very diverse behavior, even though the policy is the same. Like it can hop, it can walk. And yeah, so the same policy adapts to different shapes depending on the shape of the robot. So this can show a very different gait here. If you compare, this is the same thing. It's just showing different behaviors across different shapes depending on the shape of the body. Let's see generalization to some new agents. So if you see agents from the same distribution but held out, it can generalize zero shot really well. But this is expected because it was already working well in the previous cases. So we wanted to test, can we really zero shot testing on out of distribution examples, like very different robots. And so what we did, we really went crazy and tried to modify these robots in many different ways to see if our policies can still generalize. And if you, so it doesn't excel here, like it is not running forward like fast, but it is still able to adapt decently well to a wide variety of robots here. Like it can, it shows a very different gaits for this robot, for this, and again, it's the same policy at everywhere. All the motors are controlling the same agent. You can also put objects. It can still balance. It doesn't excel again, but it's still a generalization. It does fail sometimes, like if you really make the problem harder, like this right one doesn't even have legs. So it is trying to use hands to move forward, but it's kind of failing. This one is like over here, the muscles are not, I think there is not enough strength to carry that weight of the body. But anyway, and one interesting thing we also found that the global coordination among these limbs actually emerges completely out of the training. Like there is something called biological central pattern generators, which biologists study, and which are common across humans and various other organisms. Like there are sine wave patterns about when you walk and things like that. These spikes can be recorded. And we found the same kind of coordination emerging in messages that are being passed through these policies. So here I'll show the variation of these messages as the training goes. Now, in the very beginning of training, the messages are completely zero because these agents have not learned anything. So it's completely flat. So the x-axis is the episode time step and y-axis is the message projection. But as the training goes, these messages start to take different shapes for different agent. So for the top row, you see two peaks because it's the walker agent, and these peaks correspond to these pose of the agent. And at the bottom, it's an hopper agent, which shows three peaks for three different poses. So basically what is happening is that these modular policies, which are learned across multiple robots, kind of like this evolutionary timeline, different agents at different time steps, it is kind of learning this internal clock, which is helpful to generalize to new scenarios. Yeah, and but is it even possible in real world? Well, in fact, there are actually already robots which are modular and self-assembling in real world. It's just that they are controlled by some person manually using a controller. And what we are learning is a software to drive these robots automatically. And we also have our own ongoing attempt with these modular robots where the motors are shared everywhere. And here is one example of that. Okay. Yeah, in the interest of time, I'll skip some of the quick things which I was going to talk about. But we do have something where we are trying to study the notion of curiosity also in children and see if this captures the behavior that children show in things. And again, we are also interested in 3D perception. Like, can you, given a single image, humans can imagine what is behind the image. And we are developing approaches which can actually, given a single image, just imagine everything else about the environment. So this is all generated, and only the first image was input. Yeah, and I'll not go into the approach, but yeah, this kind of approach is generalized to very difficult scenarios like this case, single image as input, and you can imagine what is going on. So these are all part of the bigger story in the sense that you want 3D perception, control, and exploration and all these to work simultaneously. Yes, we can also, I'll just skip this. Okay, skip. Yeah, it can work across for paintings, etc. Okay, so to summarize the approach, basically we discussed how to learn efficiently in the real world and how do we generalize across robots. I covered two aspects. One is the ontogeny and the phylogeny. Ontogeny is like algorithms like curiosity, etc., which allow the agent to learn across the lifetime of the agent, and then what can you learn across different robots that is helpful for new robots at testing. Yeah, with that, thank you. Sorry, I think I went slightly extra. Okay. And I see Natasha is here already. There is some noise coming from.
It's coming from Natasha's screen. Natasha, we can't hear you.
I think in your microphone, Natasha, there's some noise in it. Yeah, first of all, thanks a lot for your talk, Deepak. It was really, really interesting, very exciting research.
I think there is some noise coming whenever, Natasha, you are unmuting.
How about now?
Now it's perfect.
Okay, perfect. Sorry about that. All right, great talk, Deepak. That was awesome. Can you guys see my screen?
Yes.
Cool. Should I just get started? We could do questions at the end. Is that the plan? Or?
Yeah, let's do that. Unless anyone has like a really specific technical question right now about the previous talk. Otherwise, more general questions we can just put to the panel discussion. Okay, I think otherwise, yeah, I would like to extend a warm welcome to you, Natasha. Natasha received her PhD from MIT, and now she works at Google AI and in the Berkeley AI research group. And she's doing super interesting work on social and affective intelligence, introducing an often overlooked factor in learning through social interaction from social cues or using social influence as intrinsic motivation. And yeah, I'm excited to hear your talk.
Great, thanks. Well, thanks for having me. And I think there's going to be some interesting overlap between the motivation behind what I'm working on and what Deepak just presented. So it's a lot of fun to see that. So I'm going to be talking about social reinforcement learning. And to give a little more context on what I mean by that, in humans and animals, social learning, which is the ability to pick up on cues from other agents in your environment and learn from them, that helps humans and animals rapidly adapt to dangerous new environments. So even this little 3-inch stickleback fish, when it's dumped into a new and possibly dangerous environment, can use cues from where other fish are gathering to decide where there's a safe source of food. And similarly, birds can actually learn complex behavior from observing other birds. So actually, this was an example in the UK where birds learned to open milk top bottles, and this actually spread socially. So that's quite interesting. But of course, humans have basically taken this ability to the next level. So a lot of authors have argued that what really separates humans from other animals is our impressive ability to cooperate and infer the intentions of other humans and share knowledge. And so that's kind of led to our cumulative cultural evolution and was possibly a driver behind our cognitive development. So basically what I'm going to ask in this talk is there anything that we could take from this in terms of how social learning or learning from other agents could help reinforcement learning? And I think it might be able to help RL agents adapt to new environments, learn more complex behavior, and coordinate better with other RL agents, obviously. But also, it could help coordinate with humans. So potentially, social learning abilities could help improve human AI interaction as well. So that's basically what I'm going to be talking about today. And I think you already mentioned in introducing me, thank you, like it's obvious that social reinforcement learning could help improve multi-agent coordination and communication. So that is something I've worked on in prior work. But I'm actually not going to be talking about that today. I'm going to be focusing on two new ideas. So basically using multi-agent training or social learning as a way to improve single agent learning and generalization. So can some type of multi-agent training regime actually improve just normal RL? And then the third point is, of course, improving human AI interaction. So doing social learning from a human. So I'll talk about how to do that. So let's get started with this first part. So single agent learning and generalization. So this is a paper we just presented at NeurIPS, which is joint work with Michael Dennis. And I think Deepak already gave a lot of the intuition for why this is important. We know that DeepRL can work really well in environments where we have a simulator that completely describes the problem, so games. So we can simulate every aspect of something like Go or a video game like Dota, but of course, when we don't have a perfect simulator and we want to do something in the real world, DeepRL gets a lot harder. And it's actually, as Deepak pointed out, pretty bad at generalization. Generalizing to things outside of the environment that it was specifically trained on. And so one approach that people have taken to correct for this deficiency is just say, well, let's widen the training environment. Let's randomize all the parameters of the training environment as broadly as we can, and then train on that and hope that that's going to cover whatever experience we're going to encounter at test time. But actually, if you look at how well this approach works, even in very simple environments, we can see that it can kind of break down. So here's an example where we're trying to train this little blue agent to get to this green goal and navigate around these obstacles. And the environment is partially observed, so it can only see what's in this blue square. And we can use domain randomization to randomize the positions of the obstacles and the goal, and we can train on that distribution of environments. But then we can test whether it is able to transfer to this classic 4 rooms environment, where now the obstacles have a specific configuration, which is that of walls. And it turns out that this agent actually hasn't learned to walk around walls, even though this is within the distribution of things we could sample with domain randomization. It has a specific structure that's unlikely to be sampled. So the agent didn't focus its training time on this and is not able to perform this transfer task. So I think this is pretty sad, because if domain randomization isn't working in the simple grid world, do we really expect it to work for the real world? And even if you could use it to do some sort of sim to real task, like maybe I pre-train in a simulation of stairs by varying the height and the width, and then I am able to get an agent that walks up, say, this set of stairs. If we look at what the real world actually looks like, there's just so much diversity and complexity that it's unlikely we could randomly sample stairs that look like this. So how can we actually make progress on applying RL to this type of distribution shift in the real world? So what we really need is a series of complex training environments that are going to be able to cover these unknown real-world challenges that we'll face later. But we don't want to have to program everything we could possibly encounter into the simulator ourselves by hand, because that's just going to be brittle, error-prone, time-intensive, and we're going to miss stuff. So this is not a good approach. So maybe we can take inspiration from the DeepRL that we know works really well, and in particular, self-play. So in self-play, because the agent is training against a copy of itself that is also learning, it's getting this automatic curriculum of increasingly more difficult opponents. And as the agents are opposed to each other in this adversarial setting, they exploit each other's weaknesses and correct for them. So this adversarial training seems pretty cool. So maybe we could think about using an adversary to actually generate an RL environment to train our agent. So what if we take an RL policy and actually parameterize the environment? So now our adversary is setting the parameters of the environment to minimize the performance of our agent. And this seems like a cool idea. And if we look at how well this works, we see, okay, this adversary looks like it's building kind of an interesting environment, but something is about to go wrong. It looks like it's cool, it's cool. Uh-oh. So what the adversary has done is actually just blocked off the goal from the agent. So there is no path between the agent and the goal. And this is, of course, what the adversary is optimizing for. It wants to minimize the performance of the agent, and it's done that very effectively. But this provides no learning opportunity to the agent and is just a waste of computation. So this objective is not the correct objective when the problem is asymmetrical, I will argue. And previous work solved this problem by basically manually constraining the adversary using a bunch of thresholds that are specific to each task to make sure it can't make the problem impossible. But what we really want is a more elegant way to ensure the adversary cannot create impossible environments. And ideally, we'd actually want to save computation by making those environments tailored to the current skill level of the agent, so that we get this automatic curriculum. So the tasks are always just the right difficulty. And so I'm looking at this and I'm like, well, I love multi-agent RL. So, you know, what's that saying about if you have a hammer, everything looks like a nail? Maybe the solution here is just to make this more multi-agent and just add even more agents to this problem. That's going to solve all our problems. So that's actually the idea behind the algorithm we're proposing today. So instead of just having an adversary that generates an environment which a single agent plays, we propose introducing a second agent that's going to constrain the adversary. So we take our normal player agent, we're now calling it a protagonist, and we introduce a second antagonist agent. And then the adversary is actually going to optimize for the difference between their performance. So what this does is it means the adversary wants to create environments that are possible, at least for the antagonist. The antagonist can achieve good performance, but are challenging and exploit the weaknesses in the protagonist policy. And so we call our algorithm protagonist-antagonist induced regret environment design, which is a bit of a mouthful, but we think paired is accurately describing how we're using this pair of agents. The cool thing about this, though, is we can actually relate all of the techniques we've discussed so far to the decision-making under uncertainty or decisions under ignorance literature. So we can think of domain randomization as the principle of insufficient reason, having a mini-max adversary as the maxi-min principle, and paired we can show is equivalent to training a mini-max regret policy. And all of these we are calling different forms of unsupervised environment design, which is a new formalism that we're introducing. So basically what we're doing is we're saying instead of a normal POM-BP, we're going to talk about an underspecified POM-BP. And what this is just has this additional set of parameters that take the underspecified POM-BP and assign parameters to make it an actual POM-BP. So you can think of, in a grid world, the space of all possible grid worlds is the UPOM-DP, and then the assignment of blocks to specific locations and a goal to a specific location is the specified POM-DP. So the theta is the block positions. And then you can talk about how to define a policy that defines a distribution over how to set those parameters of the environment. And depending on how you parameterize that policy, you can recover these different techniques that we've discussed. And we can show that paired is the mini-max regret policy. So we have a pretty simple proof to show that. Basically, if we just assume that the adversary and the antagonist are coordinating because their interests are aligned, then if the system is now basically a two-team zero-sum game. And if it reaches a Nash equilibrium, we can show that the protagonist will be playing the mini-max regret policy. So we think paired is doing mini-max regret, but why is that a good thing to do? Well, actually, regret lends itself very nicely to this automatic curriculum generation aspect. So regret incentivizes the adversary to create the easiest possible environment the protagonist cannot yet solve. So why is that? Well, in many RL problems, including the one we study here, there's some bonus in the reward for completing the task more efficiently or faster or in fewer time steps. And if that's the case, then we can see that the regret for an easy environment that the protagonist doesn't solve is going to be harder than the regret, or higher than the regret for a hard environment. So if the protagonist isn't solving either, its reward is 0. The reward just boils down to how well the antagonist can do. It's going to do better in the easy environment. And so this regret objective explicitly incentivizes finding environments that are as just beyond the protagonist's current skill level. And so we think of this as trying to propose tasks in the protagonist's zone of proximal development. So tasks that it can't just do by itself, but with this scaffolding, it can learn to do. And I'll give a little bit more details in practice on how this works. So what we do is we start by randomly initializing all the agents. And then until convergence, we actually have the adversary generate a set of environment parameters theta. And then the protagonist collects several trajectories in that one environment. And so does the antagonist in the same environment. And by collecting several trajectories, we can stabilize our estimation of regret by taking the max over the antagonist's trajectories and the expected value of the protagonist. So this helps keep that regret signal positive for the adversary and really emphasize environments that are possible in the best case, but challenging on average. And so the adversary maximizes that signal. And we can actually have the two agents just maximize their normal environment reward, and that seems to work quite well. So that's the idea. How well does it work? If we compare the environments generated by these different techniques, we see that domain randomization can't generate environments with specific structure, and it's not generating a curriculum. So it has those problems. As we saw before, Minimax makes impossible environments because, as again, I'll argue, it's the wrong objective. In contrast, Paired can make structured environments that are challenging. You can see there's like corridors, there's quite a long path to the goal, but they are feasible. So that's kind of the key piece there. If we look at the statistics of the environments being generated over the course of training, on the left here you see what the adversary is building for all the different techniques. And you see that no matter the statistic, domain randomization is kind of flat because it's not adapting or providing a curriculum. The most interesting statistic is probably C here, this passable path length. That's the shortest path between the start state and the goal state in the environment that's built, but it will be 0 if there is no path. And so you can see that a Minimax population-based training approach, which we think of as the most equivalent to prior work like POET, is driving this metric to 0. So it's making impossible mazes. In contrast, Paired is posing more challenging problems with a longer path length. And that actually leads to, on the right there, column D, the agents actually learning to solve more complex mazes. And what's interesting about this is none of these agents are explicitly trained on this metric. They're just trained with this environment reward and the paired objective, but this solving increasingly harder mazes is emerging from this training procedure. But what's cool about this is that what we really care about is how well do these different training procedures prepare agents to transfer to some unknown tasks at test time that they've never experienced during training. And we can see that as the complexity of the task increases from basically just domain randomization grid worlds with fewer or more blocks to increasingly complex human designed tasks, we see that the performance between Paired and the baselines also increases. So for these extremely complex tasks, actually only Paired is able to make any progress on solving these. And so we think this is a promising result, suggesting that maybe this could prepare agents to generalize to tasks at test time that developers can't necessarily foresee. And we also tested this in continuous control environments. So we basically, as previous work like RARL focused on constraining the adversary manually by defining thresholds on the force with which it could apply to an agent. But we just show that if you remove the constraints on the adversary over the course of training, this Minimax objective will predictably drive the agent's performance to 0. And then when you transfer that agent to a series of new mass and friction coefficients, that's on the right here, you see that Minimax just fails utterly. But of course, Paired doesn't drive the performance to 0. It challenges the agent so the performance gets worse, but it better prepares it for transfer to these new test tasks, even without any fine tuning or doing a lot of engineering to constrain the adversary. But this is what I'm really excited about. So when I first joined Google, there was some talk that like maybe my research should eventually have some sort of like product impact or whatever. And I'm thinking like, how are these multi-agent grid worlds really going to benefit any Google projects? But actually, Google wants to make this environment, this agent that can perform web navigation tasks for you. So the idea is basically you could say, okay, Google, go buy me a keyboard or go book me a flight to Los Angeles. And it would navigate that website, put in your information, and complete the task for you. But of course, the internet is super vast and websites are really complicated. So this is a pretty hard problem. And what the team was actually initially doing was manually defining a curriculum of easy, medium, and hard websites to try to get the agents to learn to do the harder tasks. But you can see, of course, it isn't actually solving these hardest websites. So the idea was, let's apply paired to actually generate a curriculum of websites. And of course, I think this is going to be a more scalable approach, because if you just try to collect all of the training data of all of the websites on the internet and pre-train on that, well, A, that's really hard, and B, what happens if Delta updates their website? Now you have to collect the updated website and retrain your agent. But instead, what if we could prepare our agent to be more robust to many different types of websites? So we applied paired to this approach. These are some examples, paired with some enhancements, by the way. But these are some examples of websites generated by the agent early in training, where only a few elements are on each form at a time, to late in training, where there's a lot of information that needs to be filled out simultaneously. And then we tested it on standardized web navigation environments. And we actually found that we were able to attain state-of-the-art performance on this task, where paired is able to beat both domain randomization and a scheduled curriculum learning approach. So we think that's exciting. And in conclusion, we think of unsupervised environment design as a way to think about improving transfer and generalization by describing the distribution of training environments that are preparing you for transfer. And we think paired is a good idea for UED, because by constraining the adversary with the performance of a second agent, it ensures the adversary creates feasible yet challenging environments. So that second agent acts as a flexible measure of what is reasonable performance. And then regret as an objective actually does lend itself to creating this automatic curriculum of tasks. So that's the idea here. And I won't pause for questions. We can take that at the end, but I'll jump right into the third part of the talk, which is on learning from human-AI interaction. So we might want to be able to learn from human preferences, not only because humans are a great authority on how to correctly perform many tasks, but also just because of this kind of interaction that happens all the time. So here a user is asking her Alexa, what's the right way to Walmart? And Alexa says, the right way to spell Walmart is W-A-L, blah, blah, blah. So obviously this isn't what the user wanted. And I'm going to bet you that the next thing that she says is going to be tinged with some hint of frustration, either in the tone of voice, the facial expression, or the words chosen. And it would be really nice if Alexa could actually pick up on that signal and use that to learn not to do this answer again. And we think that this type of implicit feedback is going to be more scalable than trying to get explicit training data from humans. So I often ask people, how often do you actually fill out these cards to train Google's machine learning algorithms about whether you like the results? And most people really don't bother to do this. Why should you spend your valuable free time training Google AI? So trying to get this type of manual feedback really doesn't scale. But actually getting social feedback, this is something that you're getting for free anyway. People make facial expressions, they have a tone of voice, they use particular word choices. So that signal is there. It's something they're doing naturally, if only we could pick up on it. So that the first project we did in this direction was kind of fun. Basically, we wanted to see if we could train a model to sketch better sketches by observing the facial expressions of people reacting to the model sketching. So we actually made an online platform, collected a bunch of data of people's facial expressions as they watched a sketch RNN model. And then we used that data, and there were very few samples, so we had to do a very sample efficient technique. Basically what we did was we looked at the pre-train sketch RNN, like sequence to sequence VAE, and we used the facial expressions data to just learn which parts of the embedding space of that VAE corresponded to sketches that would produce high smiling and low boredom. And then we can see how this actually affects how the model draws. So here's how it used to sketch cats before training with any facial feedback. And you can see that sometimes it makes a pretty cute cat, but sometimes they're like a little more abstract. But if we train with, I think, 69 examples of facial expression feedback data, the distribution shifts pretty significantly. We can see that this model is now drawing what I would call significantly cuter cats. Whether that's a massive scientific contribution, I don't know, but we can actually see a little bit more about how this works with the rhinoceros model. So this is how it was drawing rhinoceroses before the facial feedback. And you can see that it really doesn't get the concept of a rhinoceros at all. The drawings are pretty poor. But again, with only something like 67 or 68 samples of facial feedback, we can significantly improve how it's drawing these rhinoceroses. And so they actually look recognizably like a rhinoceros in most cases. So if you don't believe me, we did conduct a human study. Humans significantly prefer the sketches with the new model. So we seem to have correctly learned how to draw better according to human taste just from facial expressions. So this was a fun project, but we wanted to get a little more serious about this and actually learn using reinforcement learning based on these human social cues. So that's this project that we recently published in EMNLP. And the idea here is to learn from the implicit social cues expressed in dialogue. So we built this online web interface, and here you can see me chatting with one of these pre-trained dialogue models. And when the model says something that isn't really working, doesn't make sense, I can just say that didn't make sense. And we can detect that that's actually a negative sentiment expression. So we can use that as a signal that the model did something wrong, as a negative incentive. And then, of course, when the conversation is going well, we can also detect that and use that as a positive incentive or reward to train the model. So that's kind of the guiding idea behind this project, but it involved quite a few components. So before we could start with this, we had to pre-train some reasonable dialogue models using some new and existing data sets that we scraped, then put them online so that we could actually have people interact with them and collect some data from that, collect the data, and then use that data to actually develop good implicit rewards. So if I'm happy, is that a good conversation? Should I always be happy? What does that mean? And so a lot of the project focused on that. Once we had the rewards, we then trained with offline RL. And I'll explain why we need offline RL in a bit. Finally, once we have our models, we then put them back on the internet, got them to talk to a novel set of humans, and assess whether the humans liked the conversations. So I'll start with the online platform. So you've already seen a preview of that. There's some key features, which is that it recognizes the sentiment of the person and displays that back to them. And we also provide the ability and encourage the users to explicitly upvote and downvote utterances that they liked or disliked. So we have a mechanism for explicit feedback, but again, our hypothesis is that that's not going to scale as well as just learning from the cues that are present in every sentence of the conversation, because the signal is too sparse. People aren't going to break from the natural rhythm of having a chat to upvote. It's too unnatural. And then we did a lot of work to determine, okay, given that we do have some upvote, downvote data, what do we think actually is the most accurate signal of the ground truth human preferences that is implicit? So we looked at both the dialogue literature on what sort of metrics have been proposed before and the literature on human communication. So what makes a good conversation? Is it empathy? Is it active listening? And so we developed a series of rewards for that. For active listening, it's a good thing to ask questions, and that actually turned out to be one of the rewards that correlated strongly with these upvote, downvotes. So did maintaining positive sentiment, not repeating yourself, which is something that is from the dialogue literature. And then in terms of eliciting positive signals from the user, we found that eliciting laughter and eliciting positive sentiment correlate strongly with the ground truth preferences. And finally, staying on topic was pretty important. So having a high similarity between the bot's response in terms of the words and the sentence embedding of what the human said. So these are the rewards we focus on after much iteration. And then we want to actually use them to train a model. But this is actually tricky. So normally in RL, you have an agent interacting with an environment, but now we're going to replace the environment with a human. And wait, did I just say we were going to put a bunch of models on the internet, talk to humans, and then update the models based on that? Well, we've seen how that can go in the past. So we decided that it's really not safe. We could potentially learn inappropriate behaviors if we learn online from humans training the model. So we basically need to not update online, but instead update offline and then carefully test before we put those models back. So this is hard. This means the interaction loop with the environment is broken. We can't explore, which is a fundamental component of how most RL algorithms work. So we need to do offline or batch RL, which is off-policy RL from a static data set without being able to explore. And I'll explain why this is a hard problem. So let's say that I just want to do this very simple RL problem, which is get this little agent to navigate to the red flag around these obstacles. But let's say I'm doing it entirely offline from a batch of data where the probability of a state being in the batch is shown in yellow. So all of this white region is not contained within the batch data. If my model is at any time initialized or during the course of training decides that the highest value action it can take is to go outside of the batch data, outside of the support of the batch data, there's basically no way to refine that. And even worse, that estimate, because of the Bellman backup operator, will actually propagate into all of the previous states. So my estimates of all of the states leading up to going here can be arbitrarily bad. So this is a real problem. And we decided to solve it a very simple way, which is just impose a KL constraint so that the RL agent needs to take actions that keep it within the state action space that is covered by the batch data. And then it can search within that batch data for the optimal policy, even if this is slightly less probable. If the reward is tuned correctly, it should be able to find it. So to put that in math, basically what we do is we take a pre-trained prior model of what's a probable action under the batch data. And in the language case, it's obvious what this should be. This can actually be our pre-trained language model, which says how probable is a word given the conversation context. And then we just take our normal RL loss, which is optimizing for expected reward, and add this KL divergence constraint such that the RL policy shouldn't diverge too much from our pre-trained prior. And this is very simple in practice. It just amounts to adding two terms to our Q function. We subtract the probability under the RL policy, which is just like doing entropy regularization, which is good because we are trying to output diverse and interesting language. And then we add the probability under our prior. And we do some other cool tricks to make this work, which you can check out in the paper. But trust us that it actually does work. So we look at simple environments just to show that this is reasonable. This is the OpenAI gym where our method, way off policy, is shown in purple. You can see that it beats behavior cloning and prior approaches to offline RL like batch constrained Q learning. But in dialogue, it's actually pretty important. So here's what happened if you don't do the KL constraint. We see that the model, if you just learn with Q learning, starts saying things like, where did you say to me? You want to talk to you about you? So it's kind of diverging away from realistic language. It's starting to use really unrealistic sentences, and it's also just exploiting the reward function in the easiest possible way. It asks a question every utterance, and it spams as many tokens as possible to get more reward. So instead of doing this, we can impose this KL constraint, and we see that when we do that, the language improves a lot. So it says things like, hey, I hope you have a great day, and I wish you the best. So not only is it staying more realistic in terms of the language, but to optimize the rewards like eliciting positive sentiment, it's moved towards being more cheerful, polite, and supportive. So we think of this set of rewards as basically making it more Canadian. But we can look at how well this worked. So this is the elicited human reward from a set of novel users at test time. So now we've put these bots back on the internet, they're talking to new people, and we measure how much of the reward it can elicit from the humans. And we see that our KL control techniques significantly outperform the language model baseline, the batch Q learning baselines, and batch constrained Q. We can also look at how humans rate the models. And again, we see that in terms of the total ratings, the KL control models significantly outperform the baselines. And they also do get more manual upvotes and downvotes. But there is a caveat to this. In terms of the ratings, the models don't actually outperform the language model baseline. So that's kind of interesting. We think the main problem is that the RL models got a little bit repetitive because our data set was very limited. So we actually only collected 45,000 utterances. This was a university project, so we weren't able to collect that much data. And so if the task of the model is basically to search within the data that we collected for high reward conversations that are also realistic. And we just think there were too few examples of this, and this problem might be solved with more data. But I will point out that what these models are able to do is get much higher reward from the humans. So they've effectively learned to do what they were trained to do, even though this doesn't lead to better ratings. But we think this is important because you may want for production system to control specific aspects of your model, maybe to make it more polite, maybe to make it remove toxic language. So being able to correctly optimize for those rewards, even if you take a slight hit in ratings, is probably important. And then one more interesting thing we can do is look at how well these different reward functions compare. So we can see if we just train a model to optimize for minimizing repetition versus like optimizing for upvotes, which does better. And we can see that sentiment, either optimizing to elicit positive sentiment from the user or express positive sentiment, leads to the highest quality and the highest human reward. So essentially, affect is important in a good conversation, which is nice because since my PhD advisor was the leader of the affective computing group at MIT, this is keeping her happy. And of course, we found, as we hypothesized, that optimizing for those manual upvotes and downvotes, even though they are ground truth preferences, doesn't work as well. So it gets poor human reward and middling conversation quality. And we think this is just because it's too sparse. So getting that implicit feedback, even though it's noisier, because it's so ubiquitous, is able to allow us to train better models. And we've extended this work in a number of ways. So this is a project with a student, Abdul, who's great. In what we focus on here is instead of just optimizing for these rewards at the word level of the model, we also learn rewards at the sentence level by changing this conversation embedding in this hierarchical model. So this is basically hierarchical RL for dialogue. We find that it works very effectively, and especially in terms of the examples of the generated conversation. I love these. So comparing to a baseline transformer model, which has kind of diverged to just be really repetitive. It says, I don't know what that means. We see that using this hierarchical model to optimize for sentiment, it's very positive. I'm in my sunroom a lot and it's a great feeling. I'm excited. Or asking questions. We already know it can do that effectively. It can minimize repetition. So we have kind of an interesting conversation here. It says, I'm a reservoir engineer and today is my first day of vacation. We can also optimize for semantic similarity between what the user said and what the bot is saying. So when the user brings up Ed Sheeran, the bot says, what genre is it? Do you have any recommendations? And finally, I think this is what I'm most excited about. So our models and a lot of these production dialogue systems are trained on large-scale internet data and data from Reddit. And so there's a big risk that those models are trained on toxic language. And toxic language isn't so simple to detect with just stop words. We had our bot say something like, before we use this, like, oh, I'm a woman, so I just don't know what to do, right? And so it's not that you can detect that with like a particular stop word, it's just like sexist language. And so this large-scale internet data does have that problem. What we did to address this in this project is we trained a toxicity detector. So it's basically a model that scores the toxicity of generated language, and then you can use that as a reward to optimize your model against that. And so there's a cute example of this model. The user even is being kind of abusive, says, you're so stupid. The bot says, you're cute. User says, I hate you. Bot says, but I don't know why. So these are just cute examples, but I do think that trying to minimize toxicity is important, and just trying to think about the concerns of training on large-scale internet language data is important to think about. So wrapping up this project, this was the first work to propose using KL control from a pre-trained prior as a way to handle offline or batch RL. We use reinforcement learning to improve based on human feedback and find that implicit signals that we get throughout the conversation work better than explicit button presses because of the scaling factor. And again, being able to optimize for an arbitrary metric that you want to code up that describes the performance you want out of your system is useful for reducing things like toxicity, which is a problem in these types of models. So wrapping up the whole talk, basically this whole social RL direction I think has a number of benefits. So first, obviously improving multi-agent coordination and communication is key. Social learning is key to inter-agent interactions, I guess. But I think it also has a promise beyond that, which is to improve single-agent learning and generalization. and of course to improve human AI interaction. Okay, so that's everything, and thanks for listening.
Yeah, thanks a lot for your talk. Super interesting. And I'll just open the floor to questions, either to Deepak's talk or Natasha's talk, or general questions to both of them. Okay, I guess while everyone is still collecting themselves, I can already ask a question. It's to your talk, Natasha. I hope I didn't miss anything. I was just wondering, with the regret calculation, why exactly you need to train two different agent policies, so the protagonist and the antagonist. Like, if you could also use just one agent and then compute the difference between the best performance and the expected performance over multiple trajectories. So, yeah.
Yeah, so I think you could use that objective and you could sort of find things where the agent is making some traction on that problem by itself already. But we think of the second agent as a way to measure what should be possible for the agent, even if it's made zero progress so far. So it kind of widens that set of problems that you can find that we think the agent should be able to solve, but may not even be learning at all so far. Does that make sense?
Okay, but so basically protagonist and antagonist both have kind of the same skill level at all times. So you don't do anything to make sure that the antagonist is always a bit better than the protagonist.
That's a great question. We did experiment with that because you can see immediately why that would be a good idea. And actually for the web navigation paper, we do a different approach where we treat the protagonist and antagonist equally. So kind of as a population of two agents. And then we take the maximum of the population minus the mean of the population. Now, you lose some of the interesting theory if you do that. And we discuss that in detail in the appendix of our paper. So some of the assumptions are kind of violated there, but it does work better for the web nav project. So I think that's an interesting thing to do. And you can imagine expanding that to a population-based approach where you have a larger population of agents. You take the max minus the mean. So, yeah.
Okay, cool. Yeah, thanks. Oh, yeah, I think Xenia has a question.
I had a question to exactly the same point. So my question was if you thought about or if you tried extending the approach to multiple agents, so you have several antagonists. But I have another question, which is if the adversary and the antagonist communicate in any way, because I could also imagine an approach where the adversary kind of gives hints to the antagonist or something like that.
Yeah, I think that would be a really interesting extension. So they don't have a communication channel in the grid world work. We did notice something that's interesting, which is if the adversary, we had an experiment where the adversary was applying forces online throughout the trajectory. And we noticed that if it could identify which agent was the antagonist versus the protagonist, it could apply arbitrarily hard forces on the protagonist, and then the protagonist can't learn. So it's the same as the minimax problem in that case, right? So we settled on this approach where the adversary designs the task beforehand, and then both agents can play it, which addresses that.
Thanks.
Yeah, Georg?
Thank you both very much for the very nice talk. Very interesting. I want to ask a question I actually similarly asked in the earlier panel discussion, which is basically, do you think that through understanding more about multi-agent reinforcement learning for simple agents, we can actually learn how to do reinforcement learning with complicated agents in some way? And is this maybe the general path to progress from the current state?
So maybe I'll take that one, but I think it is promising. I think there's a lot that can still be learned because multi-agent interaction is so complicated, and you even just lose convergence guarantees as soon as you introduce another agent and the problem becomes non-stationary. So there's some justification for studying like worlds that can be computed more quickly because it takes so long for these systems to converge. So that makes sense. But at the same time, if you restrict yourself to really limited problems, you may miss interesting effects that you would get from a more complicated environment. So I'll give you a very simple example. I had done this work on like social influence in to enhance multi-agent coordination. So agents are trying to optimize for actions that cause other agents to change their intended actions. And we found that what the agents learned to do, because it was a partially observed world, they used this reward to actually communicate to other agents about elements of the environment that were outside the other agent's field of view. And this allowed them to gain influence. But if we hadn't studied that problem in a partially observed world, that behavior wouldn't have emerged. So there is an effect of like, if you make the problem too simple, then you might miss something that's like quite interesting. So it just depends how you personally want to tackle things, I think.
I can also chime in if this is a panel discussion already beginning or okay. Yeah. Yeah, I really like Natasha's talk and the examples she gave about the use of RL outside the grid world and all those domains, like the web crawling example in the language one. However, I just to play devil's advocate since this panel to give an opposing perspective, I also think that it is also important to kind of somehow incorporate the real world knowledge while developing the algorithms, because sometimes it may happen that there are issues or there are approaches which are out there which probably we will not even think about if we do not ground up treat the real world deployment as a first citizen in the thinking process. So the domain that I usually focus on for such ideas is robotics, and look at like ensemble efficiency or cost to failure, and all those things are several other reasons. And Natasha's talk gave a fantastic alternate real world implications like this web crawling example. Actually, web crawling is a very nice one, because I remember like years back when I gave the first Curiosity talk, somebody did mention that from a psychological perspective, they had thought of this, that how young people surf the internet in a chain kind of follows this curiosity-like behavior as well. So I'm very, very curious to know about what data speaks in that manner. But yeah, I do believe that thinking about the real world implications is important, and just is restricting and building algorithms at a grid world is not the way to go forward. And you do want to otherwise several, like one example of this is like, I think since I'm a computer vision person, so maybe I have that bias a bit strongly. For instance, in computer vision, it's very hard to get a paper in CVPR on MNIST, while that paper would not have that much harder time in other machine learning conferences, for instance. And maybe this is a good and bad thing in both ways. Good thing is that unless you have tested that idea in large scale, you do not really know whether the inferences which are held at a simpler environment level hold true or not. But the bad thing is that way you cut out many ideas which actually might be promising. So yeah, having both one leg in grid world but other leg in real world, I think is a necessary way to go forward.
I would actually have another question for you, Deepak, on the self-assembling the agents. So first of all, I was just wondering if you consider this also a multi-agent problem, even though they all learn the same policy. And second, I was just wondering the role of the messages that they send to each other, like what the crucial role is, and if they could also learn emergent complex behavior without the messages, if, for example, they have the option to learn slightly different policies.
Yeah, in fact, actually, this is, yeah, so it is actually connected to, so this is, I think, as in Natasha's talk as well, like this is kind of like multi-agent learning, improving single agent kind of story. Same story replicate being here as well. The cool part here is that, or one slight difference from maybe from multi-agent, or the way people think traditionally about multi-agent is that when these limbs combine, at least in this case, it becomes a single agent. So it's like a new entity, and no longer. So you can think of two cells combining with each other. Then it's no longer a two-cell organism. It's a multicellular organism. So multicellular and single cell, two single cells and one multicell are actually still different. So this common fate, like when you are together, then you're bind to common fate. And this is one of the biggest insights from this time in evolutionary cycle, that these things are common fate, they are combined. And that's, I think, one of the key difference. There are some examples in multi-agent literature as well where people treat it like this, but more commonly, this is not how people think of multi-agent systems. And in this common fate idea, even though when let's say there are three policies, they combine, they talk to each other, this is now an agent with three limbs. And the messages here basically becomes like a contextual guidance. So in a way, I still haven't really, this was some vague thought which we have been trying to formalize for some time now, is that the common way to, so now I'm going to the second question, by the way, the message question. So the common way people think of adaptation in deep network is fine tuning. Like I have a network, I go to new scenarios. How do I adapt? I fine tune. But there is other way of adaptation as well. Adaptation by conditioning. Like maybe I'm here, I'm used to looking at some things as input, but now I see something else. If you give me some cue, or this thing has changed this way, can I adapt? While keeping the network the same, not fine tuning the network at all. So in a way, these messages exactly play that role. So all these policies, so the sharing part is maybe a red herring. It's maybe not that important. But the key part is that same policy, which is acting at the leg, is also acting at hand, also at an elbow, in all other places, right? How does it know how to act at these places? So messages are basically a context it's providing. Okay, maybe these are learning. Okay, if you're at leg, you have to somehow apply higher torque than being at hand because you are supporting the whole body weight. And that information needs to go somehow into the policy. Over here, the messages capture the kinematic structure as well in some ways. So we never provide that the shape of the body is this 2 legs, 2 hands. It just emerges by talking to messages. So it's kind of critical. That being said, there's a recent paper which came out, a very cool paper from Shimon Wittenson's group, which kind of builds upon this work and takes it further. It's called My Body, the Cage. They do talk about and they basically replace this graph network with a transformer, a much powerful architecture, and it kind of learns very well on multiple agents. But then the key question is generalization, which I think is still questionable in that scenario. Like messages help you generalize to some new thing. If there is a configuration or setting which you've never seen, like all the results I was showing was generalization. Like our agent has 5 legs at test time. Now, if you know a deep learning, if you train on 1, 2, or 3 legs, it's very hard to generalize to very different number of legs. But with these messages, it can infer that contextual structure and still condition on it. So I think I like to believe that it is part of a bigger story, which we are trying to nail down, like this fine-tuning adaptation with this contextual conditioning. But we are not quite there yet, and it's still on this using this kinematic knowledge. But yeah.
So I guess as a follow-up question. So this morning we talked a bit about the idea of hedonistic neurons, so that each neuron in the brain is kind of its own agent, trying to optimize its own reward signal, and then together they solve kind of a team problem of the overall broadcasted reward signal. And do you think what you're doing is kind of solving a problem in that direction? And do you actually think that this is how neurons could be functioning and how intelligence could be emerging? Or do you plan to like take what you're doing right now and then add on top of that, like let's say what you're doing now would be the evolution part, and then you add on top of that like some learning part during the lifetime with, I don't know, maybe even model-based.
Yeah. So this is yeah. So yes, this is two parts. One is this model-based part at the very end, but on the neuron part, I think this is what I was hinting towards in the previous answer as well. This kind of, to me, feels like yeah. So I just make a very big connection, which again we haven't figured out properly, but this is just some brainstorming going on in our group. Like there is all this work on lottery ticket and all these like where it is found that you do train these big network, but actually the part that is doing the most of the job is a sparse thin tree in that network, which is capturing the whole that you can get the same accuracy by just pruning 95% of the network and only 5% weight do some job. And this is kind of an hint towards the fact that there is some sort of disentanglement already going on in the networks and like in neural network. Over here in the message passing, what we are doing is we are passing messages between the networks. So can you somehow connect these two within one? Like if I could replicate this message passing at a neuron level in a network, then I think it will be much closer to this heterogeneous setting which you are talking about. Like if I could train a network on ImageNet, but it has some message passing inside it, which kept maybe different parts are focusing on different part of the image. So yeah, such that if you change some image at test time, it can adapt faster, things like that. So we are kind of thinking about those directions, but it is, yeah, you're right, it is in that flavor. And model-based aspect, I think that's a very good direction, but I think that's a very complementary direction. So it's so like all these ideas are equally applicable to model-based scenarios as well. So for instance, the talk I gave today had two parts, one curiosity and one this modularity, and they had no connection to each other. Although it has connection that one is learned across lifetime, one is within lifetime, but we have not combined them together. And curiosity is driven completely by model learning and all that, while this other part was just trying to exploit modularity. So a natural next step we are working on right now is to build model-based modular systems and see if you get a flexibility of robot shapes as well as robot goals. So curiosity helps you task agnostic and this helps you robot agnostic. So can you just put it in on a new robot with arbitrary shape and perform different tasks? And over there, model-based directions are much better because they're much more efficient in task agnostic. So we are looking into that as well. But yeah.
I just wanted to jump in because I've been reading this book, Being There by Jack Clark, which if you weren't already, it's sort of a cognitive scientist perspective on, deep RL versus like symbolic AI, but it written sort of before the whole deep learning revolution. It's kind of interesting. So if you want to be radicalized that deep RL is the right approach, I think it's a good book. But it goes a lot into like decentralized control and modular systems and how like really interesting emergent behavior comes out of like just simple patterns followed by each agent, like it does like ant colonies, slime molds, all kinds of things. And they also talk about how like the early media lab, like Rodney Brooks, was actually looking at robotics that followed similar like simple protocols that led to good emergent behavior. So it might be interesting for you to check out if you have some extra reading time.
That sounds very relevant. Yeah, I'm a huge fan of Rodney Brooks, this behavioral architecture idea. Yeah, thank you.
Can you maybe send the name in the chat?
Yeah.
Yes, of course.
Thanks. Thank you. All right. Are there some other questions from the audience? Yeah, Xenia.
Yeah, so if no one else has a question, I have a very general question to both of you, because it sounds like your kind of work is very engineering oriented or very application oriented, which is cool, but it's still inspired by psychology or biology. And my question would be if you feel like that your research also goes the other way. If you have any insights that you could transfer to biology or psychology, something you learned in your kind of reinforcement learning models.
Ooh, can I jump on this one? So actually, before doing a bunch of reinforcement learning, I used to do machine learning to predict human behavior, which was a lot of fun. So we did a lot of like, can you use like a wrist warrant sensor and a bunch of cell phone data to predict if someone's going to be happy or stressed or whatever. And so we could actually, we did some interesting modeling where we sort of clustered people based on their decision boundary in predicting whether they were going to be stressed. And like the big insight there is like, the reason this problem is so hard is that there's so much inter-individual variability. Like for the same exact stimuli or like the same exact characteristics of a day could make one person feel stressed and one person feel happy. So we basically had to cluster people based on their decision boundary, and then we discovered these interesting phenotypes. Like we were looking at university students, and like some people will spend all day on campus and that's like a good day for them. If other people are doing that, that's a horrible day. So I think there is actually a lot of potential to go in the opposite direction, instead of just stealing like sort of psych things and being vaguely inspired by them and implementing something that really isn't an accurate model of human cognition at all. That's sort of the direction you can go. You can also take these models and actually use them to model human behavior and get some interesting insights back the other way. So I think that is very valuable.
Yeah, I can also jump in. So since I'm not a psychologist or a neuroscientist, so I could not say we are doing anything substantial in that area in our lab. But we are collaborating with prominent psychologists like Alison Gopnik from Berkeley. So I think that psychology as a science is very empirical, as in by human subjects, and you study their behavior. So I'm not sure if there is much to immediately transfer to that. But the way I think this can be done is this can inspire what interesting experiments can you done with human if you see some interesting behavior in AI agent. So there are like two areas, right? So in psychology or neuroscience is like there is a group of people who study actual human brain and find patterns and try to model those patterns by poking electrodes in brain or MRI and things like that. But then there is a group of people which is more recent, like Dan Yamins at Stanford or at MIT as well, Jim DiCarlo, where you can also build computational models and see if the behavior of the computational model matches the primate behavior or infant behavior in humans. And then instead of poking electrodes in humans, you poke your models because it's much easier to poke them. It just waits. So I would say the applications of this research may go a lot farther into the second paradigm of understanding. So if you understand these networks and their behavior is very similar, then you could extrapolate, okay, maybe these things hold true, or these are the properties in the brain as well, or somewhere else. I would not say human brain, but that's a very far jump to say networks are capturing human brain right now, but maybe I'm saying this is the direction that could go to in like 20 years into the future. And that's where like one example of that I was showing very briefly at the end of my talk. We have these kids playing mazes in DeepMind lab. We made this controller, which is very Eliza, who's a student at Berkeley, she made this controller with this very soft button, so these kids can easily play and collect data, and then you can compare the kids with humans in the same environment. We also had a paper in ICML a couple of years back where we generated a lot of games that RL can play, but then we removed all these human priors, like removed key and platform, and asked MTurkers on the web to play those games with random textures. That game went viral because it was so weird to play and you cannot see any physics, etc. And over there, we did get some insights as to that human performance gets totally destroyed if you do not have these priors like platform and all those things, while RL remains the same, which kind of suggests that you humans are relying on this. So yeah, I think it's unclear what exactly can you transfer, but there is huge interaction between the two areas.
And on this new work you're doing, where you compare the agents to the children walking around in the maze, do you already have any insights or kind of interesting findings?
Yeah, well, I think what happened, this is problems which we don't face in computer science. For instance, when the pandemic happened, you cannot access kits anymore. So this whole kit data got interrupted. So what we did was we pivoted. We made this mTurk interface, and now kids don't use mTurk. So now we pivoted from kids to adults, but then the setup has to be different and things like that. So it is still ongoing, but unlike in engineering, in sciences, it may take time because of these issues, which at least I didn't foresee at all. Yeah. So it is still ongoing. We don't have data, but we have found that one interesting result I can still mention is that we found that if you use these curiosity-like methods to train the agent, the generalization that you see is more human-like if you do not have this, if you just train these goal-directed agents. Now, what we are still to do further investigation. So for instance, it is human-like in the sense that if you generalize to human-created images, it works better. But if you test on random mazes, then humans do worse, and this also does worse. So things like this we are exploring.
Cool. Yeah, thanks for your answers.
Thank you.
Yeah, I would find it interesting, I guess, on the broader picture, where you would put your approaches. So, I mean, both of you have talked about some really interesting approaches. And I mean, for example, both of you have an idea for intrinsic motivation. So for you, Natasha, you have like social influence as intrinsic motivation, and you have curiosity. And then Deepak, you've showed this really cool approach with the self-assembling agents and the shared policy. And I was just wondering, like, for example, have you ever compared the shared policy self-assembling with curiosity objective instead of like building a high tower as an objective, or where do you see your approaches in the bigger picture, I guess?
Yeah, so currently I think they are complementary directions right now. So the curiosity is exploring the generalization across task because it's task agnostic, while the modularity is currently exploring generalization across agents for the same task because it's agent shape agnostic. And now the obvious question every time is, can you combine them? And I think yes, but I think they are not quite mature that they will work because if you don't even have a body and don't even know what to do, so this is like just limbs, no goal, no body. So it's like kind of very difficult situation in there. So so we did fix task for now, where that if to stand up, if to move to the right, if to do this. But we are interested. I'm just this. There are some works like model-based that you mentioned earlier, trying to improve this modularity a bit more so that you can move to the curiosity part as well. And yeah, so it's on the horizon, but it's not quite what we've tried. And social influence is very complementary to the, sorry, yeah, go ahead.
Yeah, I was just gonna say I'm incredibly excited about intrinsic motivation. Like I think your work is great, and I really think intrinsic motivation is important to think about because like manually defining a reward function for each new task is again like, so it's not general, right? Like if you want to try to apply RL broadly, you need like general mechanisms for learning, and that's of course how humans do it, right? Like we are not told, like given a candy for every possible task we could do. We have some kind of motivations that force us to learn or like motivate us to learn. So I'm really excited about that direction as well. Curiosity, I think, is really interesting. I'm thinking about like empowerment as well and different approaches for that. And it does seem like a promising path forward in the long term.
Yeah. One thing that could be very interesting is to basically try Natasha's multi-agent intrinsic motivation thing in this modularity instead of single agent curiosity, because that might be more relevant because each of the limb are like multi-agent in some way. Yeah.
Yeah. You can also think about like, instead of just trying to influence others, also being influenced. Because again, we found like in our work that if you were being heavily influenced by communication messages, you tended to get higher reward, like you were actually listening. So we think that's an interesting finding. So maybe modular agents that are able to respond effectively to others are more effective modular agents.
Definitely.
Have you ever, Deepak, have you ever tried hindsight experience replay for these robot arm tasks that you showed?
Yes, we have tried. So the thing is, one difference here is that all the results I showed in the whole talk, including all the robot result, they were all with pixels as input. So the robot camera was looking at the table or anything and just working from them. It had no knowledge of the state space of the environment. The problem with hindsight experience replay currently in the current formulation is that it relies on the access to state space, because the way you know that you have used that you have reached your previous goal or previous, not like something from hindsight, is by comparing the actual value. But if you compare the values of pixels, it doesn't quite work, because I can go to the same space, but I might not be exactly aligned with exact same lighting condition that the pixel values will be 0, right? Maybe the sun has set, it's the same place, but it's a different thing. So it's hard to find the distance metric for that. So it doesn't work very well unless you have access to the state space. So in simulation, it works well, but if you don't have access to the state of the world, it's kind of hard to scale. That being said, we are also like one work which is currently like in some way is going to be submitted to ICML in 2 weeks, is actually about combining this hindsight knowledge with this pixel-based curiosity matrix. Yeah, I'm a big fan of hindsight experience replay, but I think the distance metric is the function, is the devil in the detail, which is many papers have tried it in the last several years, but it's still not quite there. Like in which metric space do you compare your current observation to your hindsight observation? This is the big question.
Yeah, because I've also been working with your curiosity module for a while now, and I've been thinking about trying hindsight at some point. But yeah, I guess maybe you could compare on feature space level, like maybe if you use like a neural network, some of the hidden layers.
Yeah. So it's so we are trying those things, and it's a bit hard to because it kind of relies on like knowing exactly that you have reached there, because it gives a +1 for your hindsight goals, and if you're slightly off, that +1 does not work as well. There is this paper from Sergey as well on imagined goals, which is kind of like hindsight. But yeah, I think these approaches are yet to be scaled to more complex environments.
I think Leon had a question.
Yes, I'm not entirely sure whether one can hear me currently.
Yes.
Okay, great. Sorry, I'm always a bit confused with Zoom. So basically my question is, because both of your works is kind of great examples of like how I think the big topic in deep reinforcement learning shifted from like advancing the core algorithms to like finding really smart approaches by reformulating the general idea. And one thing that kind of made reinforcement learning really easy to use and like successful in the like past 5 years, I think, is that it was kind of a plug and play thing. Like I could use generalized advantage estimation and plug it into proximal policy optimization, and just works out of the box, right? With all these new approaches, that doesn't work. So that's kind of the question I have, like for the future of deep reinforcement learning. How will that kind of work? Like, will we have more and more diverging approaches, or do you think we can still always try to combine them?
Yeah, I'm not sure I fully got the question. Natasha, you want to take the answer that?
I'm not totally sure. You mean like, I think if something turns out to be really effective, like I think we all universally acknowledge like hindsight experience replay is great, right? So then you get tooling around that where it becomes more standardized and it becomes more plug and play. So I think as certain methods like bear themselves out as consistently useful, then they will also be adapted and the infrastructure will become better, right? Like generalized advantage estimation wasn't initially built into like a bunch of open source, PPO implementations, but as it's proven to be useful, it becomes built in. I'm not sure if that fully answers your question though. Are you saying like some of these techniques are maybe more like needing, I guess for my work, I always try to move away from techniques that need to be tailored to each new problem or like need to be engineered for each new problem. And I do think that's important to do. Does that answer?
Kind of, yeah. So basically, part where you say, okay, you try to tailor them towards something where you can still reuse them with different approaches. That's kind of like the worry I currently have. Like, while I see all these awesome things, like I also see that maybe it's hard to combine them. So for example, if I see like the two approaches that you presented today, like they're both amazing, but and like they kind of push the boundaries of what we can do. But how would one combine them at any point? That's kind of the kind of question I'm pondering with.
Yeah, I think this is like research. I think this is more philosophical or like a bigger skill question. I think in the longer time horizon they will be combined, I think, as Natasha was saying. But I think currently you can see the whole push is towards things which work out of the box. So for instance, if I talk about robotics in particular, robotics has much stronger results than anyone in learning community shows. And there are robots which makes your cars, which makes your aeroplanes and everything, right? So why do we need any of this? It's just because that those robots are so specific and like engineered to do that one thing, to put nuts and bolts together. And this whole new push is actually towards algorithms which can be just deployed directly. And it's quite in a nascent stage, and I think things don't generalize as well. So that's why you don't see currently them being completely usable form everywhere. And but that's the point. I mean, this is a very early field. Like this is like in every field, the first 50 years are like this. So maybe we are in that same phase here, but hopefully someday.
Thanks.
Yeah, I think we're actually about at the end of the panel discussion. If no one else has like an urgent question right now, I would just thank you, both of you, for being here, for the really interesting talks and the nice discussion, and for answering all the questions. And yeah, thanks for being here.
Thank you, Vivian, for organizing this. It was very good.
Yes, thank you. This is a lot of fun.
All right, yeah, then I hope I'll see you around sometime. And yeah, I wish you a nice rest of the week.
Yeah, thank you. Bye.
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 Bye.